This is Official Nerd Business. Hello nerd boys and girls, welcome back to our programming series. Today we will be taking a swing at Project Euler's problem number 35. And we will be doing so using Python 3 in the PyCharm editor, as you can already see open before us. Oh, mind you, there's an update. Let's click on the update button. What's the worst that could happen? Update. Alright, so 35. I've already made the boilerplate file with the bit that runs on its own if we ask it to, with the bit that integrates with our main Py, and with an attempt number 1 blank function, empty function at this point, where all the math is going to happen. And what math might that be? Well, we have a description of the circular primes. The number 197 is called a circular prime because all rotations of the digits, whether it starts with the 1 then is followed by the 9 and the 7, it starts with the 9 followed by the 7 and the 1, and starts with the 7 followed by the 1 and the 9, are themselves prime. There are 13 such primes below 100, 2, 3, etc. And if you take a look, 17 is on there, but also 71, so if you rotate them around then you get another number which so happens to be prime. So there are 13 circular primes below 100. How many circular primes are there below 1 million? 1 million coincidentally happens to be the one parameter we put in. It's called limit and it defaults to 1 million. So if we start main Py and it asks us to give a value for a given variable, then by default that's 1 million. PyCharm wants us to restart it, but we're not gonna do that quite yet. In fact, let's get rid of the message. Alright, so circular primes. We can. This is a very fun problem because we can once again break it down into a couple of nice steps. And obviously, the first step we want to take is to get all the primes below 1 million. So for that we need our lib Euler. Import lib solutions dot lib Euler se. Because we have a couple of prime functions in our lib Euler, one specifically being e dot primes list, and this gives us a list of all the primes between the upper and the lower bound. We want to start at 2, we want to go up to, but not including the limit, and overshoot should be set to false, which it is by default. And the overshoot variable here indicates if we want to guarantee that our limit is or is not within the range of primes that we get back. So if you set overshoot to true, then this function will keep on giving us primes until we've reached the limit and then carry on to give us back one more prime. But we don't want that, we want to stop at 1 million, so the last prime in this range will be 5 9s and a 7 or something, probably. So that's that, and then we I'm also going to set up a list called ret, short for return, which will store the number of circular primes that we want. And in fact, we already know that one particular group of primes is circular by default, and that's the 1-digit primes. As you can see here up top in the description. I think personally that this is a very good description. On the previous problem we had about primes or about digit factorials. The single digit numbers were excluded purposefully, and here they are included, kind of implicitly by the example, but they are clearly shown to be included. So I think that's a very good point in this example, in this description that Project Euler supplies us with. This is a very good description, so we can see that all the 1-digit primes should already be in this list. So we can simply add them, and we can do so using a generator. Or in fact, before we do so, a little bit later on we're going to do some manipulations on the primes, and we do now have a fancy function that gives us a list from an int. But the kinds of things we want to do are best done with strings, not necessarily with lists. So instead of getting all the primes in this list, I in fact want to create a list of all the string representations of these. So I want to create a list of all strings. You've seen this pattern before, I assume. This is called a list comprehension. So everything between these square brackets defines how a given list should be built up, and assign that list to our primes variable. And what we're going to do here, we're going to take a look at every possible p in this primes list, and we want to manipulate this p a little bit. We want to cast it to string. So primes, when we execute this program, will hold a list of all the strings, string representations of all the primes within the given range. And this, we can instantiate this to be a list of all the we want all the primes that were in the primes list to be entered into red if their length is exactly 1. So now we can print our return value, and if we execute this file, we're going to execute it on its own. It's going to call run with the lower bound limit, so we're basically going to emulate the example given here. And right now our return value is not actually returned, it's printed to screen, but it should give us all the 1-digit primes, which are 2, 3, 5 and 7 as string representations, so with the quotes. And we don't return anything yet from our function, so that's the none that's shown here. Right, so far so good. As said in a previous video, test early, test often. If something were off here, if we accidentally thought that we needed everything less than 1, for instance, you just make some silly typo, or there's this weird little twist in your thinking. Can happen. It's happened to me before, God knows. Then you test this and you get an empty list where you think, wait a second, 2, 3, 5, 7 should have been in here. Oh wait, this should have been equal to. So test early, test often. Right, smooth sailing so far. This made the discrimination on the basis of length, and we're going to keep doing that. Why is that? Well, if we get a 3-digit prime and we are going to rotate this to get this prime, then we still know that the result, the rotation, will be 3 digits. And since we have a list of primes that we are interested in, and we want to check if one rotation is on that list of primes, checking it against a sublist of primes that are all of the same length will reduce the search range for matches. So we're going to do exactly that. We know how many digits are in the absolute upper limit. So we're going to cycle through 2, because we've already covered the case with 1 digit, up to but not including length of the string representation of limit. Since our limit is 1 million, 1, 2, 3, 4, 5, 6 zeros and a 1, 7 digits, but the 1 million itself is not included. This will stop at 6 digits. So from 2, 3 digits, 4 digits, 5 digits, 6 digits. We're basically going to do the same here. We're going to get a subset, which is a list. And again, we're basically going to do the same here as we did there, but for I instead of for 1. Print I and the subset. This is gonna seem a bit silly, I guess, because the only I that we're currently running through is 2. The limit is 3, given not the 1 million from the default parameter here, but we are running it from the file itself, and that starts us up with 100, so that's 3 digits. We're gonna stay below 3 digits, so all the 2-digit primes that we get, and we are printing out here under I2 is just all the primes that we get. If we set this to 1000 for now, then you see the difference between 2 and 3 digits. So here's a list of all the 2-digit primes, and here's a list of all the 3-digit primes. And we're going to get a list of 4 and of 5 and of 6 a little bit later on. I'm going to set this back to 100. And we're going to drop the print statement here. Now there's also another filter that we can add here. In a second we're going to rotate primes to see if they have this rotating property. But there's a special group of primes of which we know that they will not have this property. For instance, 29. If we take a look at 29, then its rotation is going to be 92. And we know for sure at one glance that 92 is not going to be prime. Why is that? It has a 2 in the end. Same goes for 49. Alright, 49 is not prime, but I guess 43 is. Is it? It is. Wait, 49 is not prime. No, it's not. Of course it's not. This is going to result in 34, which is also even divisible by 2, so not prime. Very definitely not prime. So we can extend this with a basically what we can do here is add a check to see if any character in this prime, and it's not prime, it's a string representation of a prime, so any character in there, any digit in there, if it's in this list of 0s, 2s, 4s, 6s, 8s and 5s, any prime that has a 5 in it, so for instance 53 is in there. This is going to result in 35, which is a 5 at the end, and any number having a 5 at the end, not being 5 itself, will be divisible. And note that we will not be getting 5 itself in this list, because that's 1-digit prime, and 1-digit primes are already included on the list over here. And that's part of the reason why we are running this from 2. That's to avoid having trouble here with the 1-digit primes. But this statement doesn't work on its own. We need to check if there's any this is basically a tuple comprehension. It's going to generate a list of this. This could have been done with square brackets as well. Currently, I'm missing something. It's going to take the prime that we are currently looking at. It's going to split it into characters, and then it's going to check if any of those characters are on this list. There's only 2 things wrong with this piece of code. Let's first introduce, if you get a long line in Python, you can, most of the time you can just press enter and continue on the next line, but there's also a special, you can add a slash to a line, and that guarantees that the next line will just carry on as if there were no line breaks in between. So it's good practice to have a slash at the end of your lines if you're gonna enter a line break for readability. And I can also suggest to actually put in a line break here, because you're doing 2 separate things. You are testing for length, and you are testing for the presence of any given characters. But this needs to be in mod. What any does is, if any of the if we have a 3-digit prime, ABC, ACB, ABC, then this list is going to have 3 entries, one for A, one for B, one for C. And if A and C are odd numbers, but B is A2, then the resulting list is going to be false, true, and false. Now we want to know if any of those hits were actually true. Then this should raise a red flag. So if this statement were true, then it would be included. So we need to negate this statement to make it false. If any of these characters that are in our prime raise a red flag, then we need to bounce it, and we do that by using not in this case. Second thing that's wrong with this code, these are numbers. C is going to be a string. This is never going to match. So we need to put quotes around all of our numbers here to turn those into strings. And then we have it. So if we were to run this code now, our subset should be a lot smaller than what we just had, because we are going to exclude any number that has a 2, a 4, a 6, a 0, a 5, etc. So let's run this. These lists are already a lot shorter. If we have a look at the primes over here, then it's beginning to look a lot like the example you already had. So this circular property, a lot of the 2-digit primes have this particular property, and the 3-digit primes are a whole different story. And as you can see, there are no primes in the 200s. There will also be no primes in the 400s, nor in the 500s, because those will have 5 in them, nor in the 600s, because 6 is also even. So we have a leap here from 300 and up to low 700, etc. So once again, test early, test often. This seems to work. Now for the next bit of code, we're gonna keep on crossing off numbers from this list. Basically that means that we need a while loop, and we could say while the length of this subset is greater than 1, but we can also just say while subset. You need a sort of if statement, you need a conditional here that can default to true or to false to continue this loop. While this condition here is true, then the loop will continue, and once it is false, it will break out of the loop. This will Python, when asked is this particular variable true or false, well, it's a list and it has elements in it, so as long as it has any elements in it, it's true, and once this becomes an empty list, it's false. So that's how Python is going to evaluate this particular thing. We could, for instance, to show how this works, I can print out the subset and then drop one element off of it. So in the case of, I've gone back to 100, so we're going to just see the list for the 2-digit primes here, which keeps getting shorter and shorter. Pop, by the way, pop is a function that works on lists and it takes out the last element. If we were interested in the last element, we could do this. We are storing the last element in X, but we are also modifying the list that pop is called on. This is absolutely nonsense at this point, but it's just to show what the while loop does. So the while keeps running and running and running. We're still printing up here. This can go too. So here we have the while loop. At the first iteration it still has all its elements, then we call pop on it. The second iteration it has one element less than it had before, we call pop on it, etc, etc, until we pop the last element, and then this becomes false and it falls out of the loop. First thing we need to do in this loop is determine what rotations any given number has. Or in fact, we are going to rotate one number, and we know that this subset always has at least one element, otherwise we would have bounced out of this this loop here by now. So we're going to set the element of our subset that we are currently interested in as this one. Now we're going to, a little later on, we're going to remove elements from the subset. In fact, we're gonna that's what we're gonna do here. And I'll show what this does in a second. But first we're gonna determine all of our rotations, and this is a bit of a complicated statement, but we're gonna run through what every little bit does in a second. This is a bit of a mean trick. Once again, I'm getting to it. Alright, this might look a bit complicated and intimidating, but basically what we're doing here, we're going to build a list of rotations, and we're going to call those R. And basically how we're going to get those rotations is by concatenating the current element that we're looking at. And why does this work in the first place? Well, let's first look at all of the rotations that we want to get. Say for instance that we have ABC, or 1 to 1, this is prime I believe. Let's state that this is a prime. I'm not entirely certain, but whatever. It's definitely not a prime we're gonna have here because it has the 2 in it. This is a more plausible example. Or the wait, this example, this is fine. So what we are basically doing when we're trying to get all the rotations, what I basically want to do is not pick the last 2 characters and then put the first one back behind it and then do this again. Now what I want to do is to get this. So we are going to take the number and append itself to it. This is part of the reason why we're working with strings here, because this is a lot easier when this is a string. The plus symbol that we use here, because this is where this is happening. The plus sign on strings just means append the one to the other. If these were numbers, then it would just do arithmetic addition, and that's not what we want. And now to get all of the rotations, we're going to start here for our first rotation, then we're going to start here for our second rotation, and we're going to start here for our third rotation, and we are each time we're going to take 3 characters. So this is rotation number 1, this is rotation number 2, and this is rotation number 3. To show you where those parts are, this is the part that says start at index number 1 and run all the way up to index number 1 plus whatever length of prime we are currently looking at. And note this refers back to this I, and this I runs over our subgroup of digits. So if we are looking at 2-digit numbers, then I will be 2. And this is going to start at 0 and run up to 2. And this is going to be repeated a couple of times because there's an inner list comprehension in the outer list comprehension, and this is looking over all of the possible values for G. So G is going to be 0 and 1 for 2-digit primes, because it's still going to start at 0 and it's going to run up to but not include the 2 here, and then the 3 here, and then the 4 here. It's gonna do this trick for every digit we are running through. And also we can add another filtering to this, because we're gonna go to rotation, and we are interested to see if that particular rotation is also on the list of n-digit primes. So why not add a check right here? So this rotations collection is going to have every rotation of a given number, where that rotation is also present in the subset that we've already created here. So the subset has all of our 2-digit primes or all of our 3-digit primes, and then we're going to pick one of those primes, the very first that's on the list. We're going to generate every possible rotation, and if for each of those rotations, if it already is on the subset, then we want it included in our rotations variable here. Said before, it's a pretty complex statement, but you can mentally deconstruct every element that's in there. In fact, I am going to add a big block of comments to this. If you will just give me 1 second, we'll be right back. Alright, we're back. So I've added a block of comments right above this statement, and I have basically what I've done is all of the actual working code is being mirrored up here, and the description of what that particular bit of code does is back here. So here we have the bit that runs through every possible starting point in our concatenation. So that's described here. Here is why we are concatenating and taking a substring out of that concatenation, and why that works. And here is the outer bit of the list where we get that rotation back into R, and then check if R is also present in our sublist. So that's the comment bit on that, and it's pretty we've been pretty lax with it throughout our solutions. They're pretty short and made for one particular goal. Usually you want to be a little more forthcoming with your comments. So that's this bit, and now if our rotations, because if we rotate the 3-digit primes, we get 3 possible rotations, and if all of those rotations are also in subset, then we will now have a list of 3 rotations. We also have a 3 in this I variable, because we are checking 3-digit numbers. So if those two match, then we have a winner. So we're gonna extend our red, so the variable that we set up here and preloaded with all the 1-digit primes, that's gonna store all of our circular primes. We're gonna extend it, not append, because that would, if we append one list to another, then the second list would be added to the first list as a separate element, so we would have a sublist with X elements. And we don't want to do that. We want to insert each item in this list into the other list, so that's extend. It's basically the difference if we have a list A with a couple of elements, and we have a list B that has a couple of elements, and we were to append both of these lists, and we would get a list with a 1, a 2, and a sublist having 3 and 4. And if we want to extend the list, then we would get the list as you might expect. That's the difference between append and extend. And we want all of our rotations to be added to our current intermediate result here. And also we want all of the rotations, whether or not those rotations led to, if we found 3 rotations for a 3-digit prime, or if we only found 2 rotations for a 3-digit prime, then we still want to remove all of those numbers from the subset, because the very first number, that's the S here, we've tested it, so we're done with it and we can remove it. And also, if we found 2 prime rotations for a 3-digit prime, then we know a couple of things here. We know that the third, if we get to the second number later on in the list and we rotate that, then we will know that that's also not going to work, because the third rotation for this 3-digit prime is still missing. So we can safely remove the second element from this list, because we have also tested that this code implicitly for 3-digit primes, 1 rotation or 1 run through this code does all 3 possible rotations, checks them all. So if we found something, or if we didn't find any circular matches, then we can still remove all the primes from the subset. All of those numbers will not be interesting anymore to see if there are circular primes. If they were interesting enough, then we've already stored them, and otherwise we can just remove them. So that's pretty much it. Let's see if we can return red here, or in fact let's print red, see what's in this list, and we want to return the length of red. So we want to count how many circular primes there are, and as given as an example, there are 13 such primes below 100. So here's the 100. Let's see what this button does. We get an error, list remove, X is not in list. We could add a breakpoint and then run to it, but this is equally fast, and we want to print the subset, and we want to print the X that we want to remove from subset. It wants to remove an 11 from this list, which it does. Then it runs again, and it wants to remove a second 11 from this list. Yes, what's happening here is that the we rotate 11, which gives us back another 11. Both 11s are on the circular primes list, and if you check, 11 is a valid circular prime, because whether the rotation of the digits doesn't matter, every possible rotation is prime, it's itself, but therefore it's prime. So when we run this code for every rotation, there's 2 rotations and they're both 11, so we are removing one 11 from the subset, which has one 11. Then we want to remove another 11 from it, and it doesn't have it. Now we could add a complicated if statement to see if this element was present on the list and then remove it if it was. We could also reduce the list to a set, so duplicates are now removed from this list, and we want to check if this runs. It does, but wait a second, we were expecting 13 primes and we got 11, or we got 14, and the problem is 11 again, right? Because when we add them, we also want to. Now note that I am converting this to set twice, and I can't do it earlier. I can't make this into a set, because then this check wouldn't be valid anymore. If we reduce the 11s in a set to only one element, then this wouldn't trigger anymore, and we would be missing out on a circular prime. So I've got this cast to set and this cast to set, because honestly I don't think we can optimize this very much further. So there's our 13 circular primes for the case of 100. Let's see if we can drop the print statement, start at main.py, and let's see if we get the correct answer. I want to run problem number 35 with the default parameter of 1 million, and it found 55 circular primes in only 0.36 seconds. If you go over to Project Euler and you enter 55 as the answer to problem number 35, you will get a green check mark. Yes, we've done it. This only needs one attempt really. It's pretty complex bit of code. A lot is going on. So once again, once you look at it, it's pretty concise, but there's a lot going on under the hood. So take your time breaking down problems. Test early, test often, and see what steps you need. So here breaking down is not testing every number in the range up to 1 million, but testing every prime in the range up to 1 million. That reduces our problem a lot. Then check to see if there are other shortcuts we can take. So we know that a rotation of a 3-digit prime will lead to another 3-digit prime, so we can break down the problem into groups of digits. And once we are breaking down these numbers into groups of their lengths, we can check at the same time to see if every possible result will be valid. Now we know that results, that numbers having a 2 or a 4 or a 0 or a 5 in them will be invalid, so we can exclude those. So that again reduces our search range, reduces the number of computations we need to do when we later on actually test those numbers. And this is a bit of a kicker, and I hope I've explained it thoroughly enough, the way that we are concatenating the strings here together to get these rotations by taking a starting index just one further every time from the concatenation, then making those into a separate list of rotations, while at the same time checking that every entry in that list is also a n-digit prime. And then again removing those elements from this loop construction to eventually have this run into a false state and leaving it and getting the next I and building up this list again and then running through it again for 4-digit primes, then 5-digit primes. That's it. I've really enjoyed working this one out, and as said before, as said again and again, breaking this down into smaller steps. I hope you've enjoyed it as well. Note that this code will be on my GitHub, so check that out if you would like to watch a particular bit back there. And I hope to see you again for problem number 36. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.